Hi, welcome to my presentation. I am Danda from the University of Ottawa, Canada. My presentation today is about the unimportant role of F0 or pitch height in registrogenesis in Southeast Asian languages, new evidence from Rook and Arem. In this study, I will argue that in register languages of the ADR, there is a general tendency for the pitch on the following vowel to be higher in the register derived from voiceless onsets than that from voiced onsets. However, this pitch difference is optional and might not be a phonetic property of the register contrast. First of all, some background information. It is well established that the process of onset devoicing alone could lead to different outcomes in Southeast Asian languages. Firstly, the devoicing of voiced onsets and their merger to voiceless counterparts can give rise to the two-way tonal contrast of low and high tones in the languages of Khmer, Austroasiatic, and Kultur Tibeto-Burman. However, more common in Southeast Asian languages is the formation of tone systems from the neutralization of final laryngeals. This is the phenomenon to which the words tonogenesis were firstly designated. And then a merger between the series of voiced, voiceless unaspirated and voiceless aspirated lead to the doubling or tripling of the number of tones in those languages. So, onset devoicing in the languages lead to tonal splitting, but not tonogenesis per se. The last, but might be the most characteristic outcome of onset devoicing in Southeast Asian languages is the formation of what's called register contrast, whose phonetic implementation includes more than just F0 difference on the following vowel. Frequently attested phonetic correlates of the register contrast could be summarized in the following table. The register derived from voiceless onsets is usually called high register, and voiced onsets low register. They also have many other names. The high register has a higher pitch than the low register. It also has a tensor or modal phonation compared to the low register's lax or passive phonation. Vowels in the high register are lower than in the low register. They are also more peripheral in the former. The high register also has a shorter duration for both vowel and Vietic, voiced times of onsets. Note that languages are different in the number of phonetic properties and the relative weights of these properties they choose to signal the register contrast. In this study, I specifically look at the pitch difference between the two registers because there are different positions on its role in register contrast and registrogenesis. On the one hand, the F0 difference between the two registers, namely its being higher in the high register than the low register, is always listed when the two are described or compared to one another. However, many mention that F0 is not a compulsory or primary cue in the register distinction. On the other hand, Luang Thongkum, an Austroasiatic specialist, claims that pitch differences between the two registers are always present, even if it has always been ignored or unheard by Mon-Khmer specialists. The discrepancies regarding the presence or absence of F0 difference in register contrast is because until quite recently, the descriptions of register contrast in the languages are mainly based on researcher auditory impression. Or if it is experimentally studied, many factors such as vowel, speaker variation have not been taken into consideration. Therefore, I'd like to contribute some little effort to solve this long-standing puzzle. To do that, I looked at two Vietic languages of the Austroasiatic family, Rook and Arem. These two languages are spoken in the mountainous area in central Vietnam. They are two language sisters of Vietnamese. Arem has been described as a register language, differentiating the two registers by vowel quality, phonation type, and pitch differences. Its primary cue is vowel quality, where the original vowel system was doubled or in some cases tripled as a result of the onset devoicing process. Factors assert that there is an expected pitch difference between the two registers in this language. On the other hand, Rook has been described as having four tones differentiated by pitch height, pitch contour, along with vowel quality and phonation type differences. I will provide more details later when we take a closer look at this language. In the summer of 2019, I recorded 20 Rook speakers and only 5 Arem speakers. Unfortunately, Arem is recently on the verge of extinction. There's only 10 older people who can use their native language nowadays. The word list for Arem includes words being combination of 5 onsets, t, k, t, r, l, with 3 vowels, e, u, a, and the 2 registers. For Rook, I looked at its 2 tones in syllables standing in the glottal fricative h only, because this pair of tones exhibits an unexpected F0 pattern. Initially, this was not my main study purpose, so that I recorded 4 words only. But I think the data might be enough because of having 20 speakers. I will definitely investigate this phenomenon in more vowel context when I could again go to the field. For both languages, the word list with different randomization orders were recorded 4 times per speaker. I recorded electroglottographic and audio data, but electroglottographic EGG data has not been analyzed yet. I used phonetic grid to annotate the data, marking relevant boundaries between onsets, vowels, and coders. Acoustic measures were extracted using PRASOS, a script written by James Kirby. Time and measures were then normalized. For statistical modeling and testing, I use GAMS, generalized additive mixed model, to capture nonlinear relationships of this time-varying data. This study focuses on the fundamental frequency or F0 difference between registers or tones. I also compare phonation types between the 2 pairs of registers and tones using special tilt measures such as H1-A2, H1-A1, and step-chord preprominent CPP, because they give the same results, so that I will report H1-A2 only. For vowel quality, I will present the results for the first 2 phonemics, F1 and F2. Times does not allow me to give the complete illustration of other acoustic measurements such as VOT, vowel duration, etc. Now move on to the results. First for Arem. First of all, I looked at vowel quality to verify the previous claim on the difference between the 2 registers. This graph shows the grand means of the 3 vowel territories in the 2 registers. The high register is in blue color and the low register is in orange color. The triangles mark the beginning of the vowels. It could be confirmed that throughout their time courses, the 3 vowels are different in the 2 registers, being higher in the low register. The F1 difference is largest in the vowel A. F2 difference is most apparent in vowel A as well, where it is moved further back in the low register. This graph shows individual characteristics of the 3 vowels in the 2 registers by the 5 speakers. It confirms that the vowel differences between the 2 registers are consistent across these speakers. Now, this graph shows empirical data of F0 in the 2 registers by vowel and speaker. Thin lines in the background are individual F0 characteristics. Thicker lines are the average means of each category. Some pattern can be observed from this graph. First, in the vowel R, there does not seem to be an F0 difference between the 2 registers in all 5 speakers. We can see that the 2 lines overlap throughout the vowel duration. In the 2 vowels E and U, the pattern is of a mixed kind. There are some cases where F0 is higher in the low register, but lower in some other cases, or there's no difference at all. Speakers also vary in their F0 patterns. Given these vowel and individual variations, GAMs were used to test the significance of register effect on F0. The upper panel of this graph shows GAM predicted F0 of the 2 registers by vowel. We can see that the predictions capture the patterns we have seen in empirical data. For example, the mostly identical F0 contours of the 2 registers in the vowel R context But what's important here is the plot showing the F0 difference between the two registers. We get this by subtracting the F0 in the high register from the F0 in the low register. A difference is statistically significant if the ribbon around the line does not touch the horizontal zero line. The significant intervals are marked by vertical dotted red lines and the red color on the x-axis. And we can see that in the vowel E, the low register has a significantly higher F0 than the high register for more than 90% of vowel duration, with a maximum of 20 Hz difference around the vowel middle. The difference is in the same direction but not significant for vowel U, and there's no F0 difference in vowel R whatsoever. So what's about phonation time difference between the two registers? This graph shows the GAM's predicted values and differences in terms of H1-H2, an indication of phonation types. A higher H1-H2 indicates a breathier phonations. The low register has an unexpectedly higher H1-H2 in the two vowels E and U throughout the duration, with a maximum difference of around 8 decibels at the onset of vowel E. Again, there is no difference in vowel R. To summarize, in Arem, the vowel R has the largest vowel quality difference between the two registers, but there is neither F0 nor phonation type difference. The two vowels E and U have smaller vowel quality differences, but they are also differentiated by phonation type. We have breathier phonation in the low register versus a more modal phonation in the high register for the two vowels E and U. F0 does not seem to be a register cue because it's limited to vowel E only. And recall that the 5 speakers are all different from each other regarding the F0 pattern in this vowel context. Now move on to Rook. This language has a 4 plus 2 tone system, and these tones were presumably formed as follows. In the beginning, the language had a two-way contrast of onset voicing between voiced and voiceless onsets, and a three-way contrast in the coda position between a final glottal stop, a final glottal fricative, and other non-glottal codas. And the language had no tone, but of course, F0 perturbation and other perturbation due to articulatory effects from onset voicing and the final laryngeals. Then the final glottal stop was lost, and its effects on the preceding vowels F0 were transphonologized into a non-level tone, in contrast with the default F0 characteristics on the other types of syllables, the tonogenesis generally. And then the process of onset voicing happened, doubling the number of tones up to 4 tones. This is tonal splitting. The final glottal fricative is preserved, and tones in these syllables are treated as allotone of tones in open syllables. One of my recent studies showed that in Rook, tone is not just pitch. Rook has a consistent distinction of phonation type and vowel quality between the tones derived from voiced and voiceless onsets, as what we have seen in the table of phonetic correlates of registers at the beginning of this presentation. In this sense, Rook is a link between tonogenesis and registrogenesis. There are not many languages with this many and consistent of register correlates from tonal splitting. For a similar case, readers are referred to Mazudong and Michel's study on Tamang, a Tibeto-Burman language. However, what's interesting here is that the two tones C1 and C2 show an unexpected F0 pattern. As you can see here, F0 is higher in the tone C2, the tone derived from the voiced onsets. This graph represents F0 characteristics of the two tones by 20 speakers. We can observe a lot of individual variations. For example, females seem to have a higher F0 in tone C2 than tone C1. Males exhibit both directions. And we have an outstanding high F0 in tone C2 at vowel onset for this speaker. The GAM results show that the tone C2 has indeed a significantly higher F0 than tone C1. The difference is almost throughout vowel duration with a maximum difference of 10 Hz near the vowel middle. However, given the huge F0 difference between tones in two other pairs of A1 and A2 and B1 and B2, for example, the difference between tone A1 and A2 is around 70 Hz, one wonders if this 10 Hz difference is perceptible and used by root speakers as a tonal cue. Again, the results for H1 and H2 of the two tones show that they are significantly different for the first half of the vowel. That tone C2 has a breathier phonation than the tone C1. The maximum difference is at vowel onset of being 10 decibels, larger than what we saw in the Arem data. The vowel R is also clearly differentiated between the two tones, by which in the tone C2 it is more closed, having a lower F1, and more fronted, having a higher F2. These differences are largest at vowel onset and gradually decrease into the middle of the vowel. The vowel in syllables with tone C2 is pronounced as falling on like a. This vowel distinction is consistent across speaker. To summarize the root data, we saw that F0 show unexpected values in the two tones C1 and C2. The tone C2 derived from the historically voiced onsets, but its F0 is higher than that of tone C1, the tone derived from historically voiceless onsets. However, the tonal contrast is further realized by other cues in the expected direction of register correlates. They are vowel quality, phonation type, vowel duration differences. The results from Brook and Arem data force us to reconsider the roles of F0 in registrogenesis and tonogenesis in Southeast Asian languages. Firstly, the contrastive F0 is not the only or frequent outcome of the onset voicing in the languages. We have already known that the process can lead to tonal splitting or registrogenesis, whose phonetic properties include not just pitch, but vowel quality, phonation type, vowel duration, and Vietic differences. Secondly, F0 is more likely to be transphonologized into being a primary or secondary cue of the contrast if the language already has some forms of F0 modulation prior to onset voicing. For example, the precedent of tonogenesis from final laryngeals to tonal split by onset voicing. Even so, F0 could be later undermined if other phonetic cues are enhanced. For example, in Standard Khmer, all register properties but vowel quality were dropped, and this language has a retracted vowel system nowadays. Although not being in production cue, F0 could be used as a perceptual cue of the register distinction. For example, in trial of Banneric language or through a Chamic language of the Austronesian family. All of this therefore raises the following question. Why are vowel quality and phonation type differences more robust in tonogenesis and registrogenesis in Southeast Asian languages than in other languages of the world? Is it because voicing contrast in the languages has very different properties or even different natures? To answer this question, we need to study both onset voicing and register contrasts in a more detailed and systematic way. To conclude, the evidence from Brook and Arem show that F0 is not even a cue in register or tonal contrasts in the two languages, contrary to the previous claims on the consistent and important roles of F0 in Mon-Khmer languages. Register and tone are not just pitch, they are constellations of F0, phonation type, vowel quality, vowel duration, VOT, etc. The study of the register, tone, registrogenesis, tonogenesis needs to take into consideration other linguistic and social factors such as vowels and individual variation. This study was partly supported by grants given to Professor McQuinnell by the Social Sciences and Humanities Research Council of Canada, and to Professor James Kirby by the UK Arts and Humanities Research Council.
อะไร ลอยตีปะกระเบือตาตา